Hello, welcome to a video on the conservation of momentum in one dimension. So the first question we might have is, what is momentum? And if I'm trying to give you the most generic overview of what momentum generally is, it's basically a way of modeling how velocity and forces are affected by collisions between particles. If we're trying to calculate what momentum is though, luckily there is a very handy and easy equation that we can use to calculate it. Momentum is equal to the mass of an object, measured in kilograms of course, times by its velocity, which is of course measured in meters per second, so therefore the knock-on impact of that is momentum is technically measured in kilogram meters per second. What a catchy unit that is. Anyway, therefore, the way of remembering this equation, people often notate this as rho equals mv. That letter over there looks a bit like a P, but it is the Greek letter rho. It's a letter we've also used in statistics before for correlation hypothesis testing, if you've come across it then. So just to be aware, it's not a P, but it looks similar to one. So that's how we can calculate momentum, but how is it useful in the context of a question? Well, this is where what we call the conservation of momentum comes into play. The conservation of momentum law states that the sum of the separate particles' momentum before a collision is equal to the sum of the separate particles' momentum after a collision. So therefore you can work out the total momentum of all the objects in a particular scenario, both before and after a collision, and you know that they should come to the same thing. And so with all that said, let's have a go at an example. So we have two particles A and B that are lying on a straight line, and that's just basically just telling us in lots of words. This is a one-dimensional question, so we only have to worry about forwards and backwards for this scenario. So let's call this one A, let's call this one B. Particle A has a mass of 4 kilograms, so we can represent that in our diagram. And it's travelling at a velocity of 7 meters per second towards B, so therefore that would be 7 meters per second in this direction. Now interestingly, I've done an arrow coming out of the object, which is normally something we reserve only for forces in a force diagram. But because there's no forces that we're having to deal with at the same time as us dealing with velocities, that's why I'm a bit less stressed about following conventions about exactly how the arrows are drawn for these diagrams. It's just me representing the information that's given to us in the question in a more intuitive visual way. Then we're also told that B is travelling at a velocity of 3 meters per second away from A. So therefore that's in this direction, and therefore labelling that 3 meters per second. And B apparently has a mass of 5 kilograms according to the question. The two particles then collide, and after the collision, the particle A is now travelling at 4 meters per second. You see, this is the interesting thing about these questions. The information changes before versus after the collision. So therefore it's often in your interest to do a separate diagram for what's going on before versus what's going on after the collision. Just because then it makes it a lot clearer and easier to see what's going on, because you're not trying to slam all that information into just one single diagram, which then makes it all horrible and messy. So therefore doing A and B again, but now we're saying that A is travelling 4 meters per second in the same direction as it was travelling in before. So therefore 4 meters per second that way. We don't know the velocity that B is travelling at, and that's because that's what we're trying to find in the question. So for the moment, let's just say it's the velocity V. Nice. Okay, so now we can actually start trying to solve the question, and to solve it, we're going to use that idea of conservation of momentum. We're going to work out the total momentum before. So before the collision, the momentum is going to be equal to the momentum of A, which would be 4, which is its mass, times by, well, we're dealing with velocity. So something you've got to do as part of these questions is decide your positive direction. So I'm going to decide my positive direction as being to the right. So that means as 7 is going to the right, it's going to be a positive velocity in my calculations. So 4 times by 7, and then I'm going to add on the momentum of B. So the momentum of B before the collision would be its mass times by its velocity as well. And that, of course, would get you 28 plus 15, which would be 43. Then doing the same thing for after the collision. So after the collision, we can work out the momentum. And so therefore that is going to be 4 times by 4 because the velocity is now 4, and then for b, we've got a mass of 5, but then a velocity of just v. So therefore, we're just going to be left with 16 plus 5v. Because of the conservation of momentum, we know the momentum that was going on before the collision must equal the momentum that was going on after the collision, and therefore this is now an equation that we can just try and solve. So therefore we're going to get 27 equals 5v, and therefore v will equal 27 divided by 5, which is just 5.4 meters per second. Nice. First example done. On to the second example, and the reason for this second example is because I want to make a bigger deal of why it's important to take account of a positive or negative direction. So this time we've got particle A of mass 8 kilograms. The question doesn't say, but again, it's a one-dimensional question because all the questions in this video are going to be like that. So you have A, which is 8 kilograms, and it's traveling at a velocity of 5 meters per second towards B. So we draw another particle B, say it's over here, and then A is traveling towards B. So therefore that is 5 meters per second towards B. B is traveling at a velocity of 9 meters per second towards A. So therefore they're heading directly towards each other. And B has a mass of 2 kilograms. And then we're told the two particles collide, and therefore again we're going to do a before diagram and we're going to do an after diagram to make things nice and clear. So after the collision, A is traveling at 1 meters per second in the same direction as before. So that makes life nice and easy. 1 meters per second, A, and then we've got B over here. We've got to find the speed of B after the collision. I don't know what direction B is going to be traveling in after the collision. I don't know if it's going to be to the left or to the right. And so again, this is another aspect that will be affected by positive and negative direction. I'm going to assume it's to the right, but that is an assumption, and I might be wrong. If I'm wrong, my value for V will end up being the opposite direction to what I said, or negative basically. It's telling me that I got the direction wrong, effectively, if I end up with V being a negative value. So, therefore, same approach as before, but in order to do this question, again, you've got to decide your positive direction. So I'm choosing right as my positive direction, and that's important because it means that if I calculate the momentum before, it now means that it's going to be calculated as 8 times by 5, the momentum for A, but then I'm going to be adding on the momentum for B, but the momentum for B is going to be 2 times by -9, because the velocity of B is going to the left, and I said right is my positive direction, left therefore means I've got to treat the velocity as a negative value. So that's interesting because it means some of the momentums are effectively cancelling out with each other as part of this calculation. So we're ending up with 22 as the total momentum beforehand. So therefore, after the collision, now doing the calculation for that, we end up with 8 times by 1. And then we're going to add on 2v. So therefore, we've got 8 plus 2v. Nice. Therefore, by conservation of momentum, although we've done this extra funky stuff with the positive direction included in the calculation, we still have the idea of conservation of momentum taking place. So therefore, we can solve this equation, and if you do that, you'll end up with V equals 7 meters per second. Now, because I got the value of V being a positive value, that's good because it means I guessed the correct direction. If I'd got V as negative, as I said before, that just means I guessed the wrong direction in my diagram. Nice, the question did say speed, so actually if I had got a negative value, I would then also just go, well, ignore the negative sign because speed doesn't care about direction anyway. Nice, example 2 done. I've got one more detail I want to tell you about in this video though, and that is the key word of coalesce. Coalesce means, or effective for the sake of mechanics, it means when multiple objects are coming together and then they're basically almost sticking together. They're combining in a way that allows you to treat them as just one big object. So from a visual point of view, I'm talking about, let's say we've got two objects, A and B, and then they could be doing something that results in them colliding, And then once they've collided, if they are coalescing, that means that they are then going to travel together as one big object. Cool. So therefore, putting that into practice with this example, we've got particle A has a mass of 3 kilograms. So therefore, let's write that down. And it's traveling at a velocity of 4 meters per second towards B. And then we've got B traveling the same direction. So therefore, traveling to the right as well. And it's got a velocity of 1 meters per second. And it's also got a mass of 3 kilograms. Okay, so that's before the collision. And then after the collision, we're told they coalesce. So therefore, we can group them together as one big object. Together like this. AB, so therefore they're both going together with the same velocity. We don't know that velocity, so again, let's just call it V and then solve to find it. So before the collision, therefore the momentum is going to equal 4 times by 3 plus 1 times by 3, or 3 times by 1, however you want to write it. And therefore that is going to be 15. And then after the collision, this is where it gets interesting because of the fact they coalesce. Therefore, working out the momentum for the object in this scenario, as I said before, we're going to treat them as one big object. So therefore, instead of viewing them as separate objects with individual masses of 3 kilograms, we're going to view it as one big object with a mass of 6 kilograms, the two masses added together. And that one big object is therefore traveling with a velocity of v, so therefore the momentum after the collision is just 6v. So therefore, we can now again set up the equation using conservation momentum to then solve to find what v is. So v is going to equal 15 divided by 6, which is just, of course, 5 over 2, which is 2.5 meters per second. There you go. So that is conservation momentum. That's really genuinely how easy it is. I love topics like this that just crop up because ultimately it's such simple maths, but they count as maths. So hooray, easy calculations for the win. That will do us for today. I'll see you in a future mechanics video. Goodbye.